Yes, so I have actually to give you a slight correction from yesterday's lecture. Of course, I sometimes write one thing and I mean another. So, of course, this is so the axiom potential. Of course, the potential I wrote yesterday, which just a cosine, doesn't have a minimum at 0. So I guess you have seen it already today also in the exercises. The real axiom potential you can write with a 1 minus cosine. And this, of course, it's the correct expression and has a minimum at 0. The rest I described and discussed yesterday, it was actually correct because the formula were correct. And you see, if you derive this one, you get exactly the sign that I was using for the equation of motion. So this expression you can write in a simpler way, forgetting about, if you want, instead of using lambda QCD, using the mass of the axiom. So this form is the usual MA square FA square 1 minus cosine. And this form is actually very nice. First of all, because you see immediately the mass of the axion. And if you expand the cosine, you find out that this is exactly physical mass. But moreover, you see that in this case, you can generalize to any particle, not only to the QCD axion, but to any pseudoscalar particle with mass derived from any possible scale. So where this doesn't have to come from lambda QCD. So in that particular case, if you have a generic axiom, so you can generalize to Alps, which are axion-like particles, where you have generically the mass is not related or to FA and the QCD scale. So you can assume that take as a free parameter. Of course, you could take as a free parameter the lambda instead of taking lambda QCD some other scale, but it's much more convenient to take as a free parameter the mass of the axion and the scale of the coupling, which is FA or Fi, as we'll use in a minute. So for a generic Alps, I have the potential, which I can write in a very similar way, but with no relation between the mass and FA. So I have in principle an F squared, Fi squared, 1 minus the cosine. Okay. And of course, all the misalignment mechanism I discussed last time works perfectly fine also for any pseudoscalar. So you were just using the fact that you had this potential, and of course, therefore, the prediction I gave you yesterday, you can extend also to any misalignment mechanism to any pseudoscalar field. And actually, as it was also mentioned, I think yesterday in one question, you do not really need absolutely the mass of this Alp particle to be 0 in the very early time. It is actually enough that the mass is smaller with respect to the Hubble parameter and everything will work exactly fine. So in that sense, you do not need to have a strong group which becomes confining only after the very low temperatures. You could also think about the scenarios where you have the mass of the Alp also generated at higher scale. And these would still work. So in that sense, then you have a density again of Alps, which is again proportional similarly of what we did the computation, only that now you cannot write everything just a function of FA. You have also dependence on the mass. And in particular, you have the dependence on the mass at the time of, if you want, where the mass is equal to the Hubble parameter, which I call is TH, and of course the mass today. If you remember, the number density was coming with this parameter. Instead, the T to M today is what give us the number density today. Times, of course, in this case, you have a phi, f phi squared, and in particular also here a theta, so an initial theta squared, which also we don't know. And here again, this mass is again, the condition is such that this is equal to the Hubble at that. So this is exactly the value of the mass at the time where the field starts to oscillate or starts to move. And it's clear that it depends a bit on the model. So this mass could, as in the case of QCD, be not constant, so change with temperature, and for example, also be zero at early times and then switch on slowly. But it could also be that this was a constant. So in that sense, depending on the behavior of the mass, you can have slightly different regions, of course, which give you the dark matter density. And as usual, we have a dependence on f phi, and a dependence on theta. And you see that in some sense, if you assume that these two are actually constant, so that you have a dependence on m square f square, so which means that you have always a band in the plane m mass versus fa, which gives you the correct omega h square. So in some sense, for constant mass, we obtain, if you want, a relation for setting the right omega h square, we get a kind of band in the plane m phi. So, or f, or I mean, it depends. You will see it in a minute later in the slides. What is usually plotted is actually the coupling to the photons often, and the coupling to the photons is 1 over f instead of f. So if you couple, yeah, you have the plane 1 over f versus mass. And this we will see it in a minute. Of course, in this case, you can change the behavior of the mass. You can change because you do not know where the mass of this Alp particle is really coming from, and you can change also the value of f phi and m phi so today. So in that sense, you have a little bit more freedom. In the case of the QCD axiom, we saw at the end everything depends only on one scale fa. Okay, so this one I will show it later on in a plot. That will highlight exactly the region you could expect to have in the case of where you're using an Alp as dark matter instead of an axiom. Okay, so this one just as a small discussion, but we haven't really completely finished to discuss the issue about production. There are actually a couple of things a little bit open, and in particular, it's the issue about the initial angle. So let me come to this important point. So what should we take for theta e, the initial angle? And this is, in some sense, you have two different scenarios. So you have, which I will discuss also more in detail later. And this first scenario is if you have the Peche-Queen symmetry broken before inflation. So if you have the Peche-Queen symmetry broken before inflation, you're assuming that you start inflation when already the Peche-Queen symmetry is broken. This means that in that sense, the value of the theta, so the value of the, if you want, of the axion, is already different in different patches of the universe. But when you start inflating one particular patch, and which is very small. And in this patch, you can assume that theta e takes one value, so one constant value, and this patch is then inflated to contain the whole universe. So in that sense, you have a single theta e. So if you want a single value of theta e for the whole universe. And it is indeed a real initial condition, so we don't know what it is. And depending on what you take for theta E, of course, you can get different values of the energy density of the universe for the axion dark matter. And you have to adjust the other parameter in some sense correspondingly. So in that sense, this is really a strong dependence on the initial condition. And this we cannot say much more. Of course, if you have the Peche-Quinn symmetry also broken before inflation, what happens is also that the axion is massless during inflation. And this we will get back to that in a minute. So in inflation. See, during, okay. And this we will discuss in a minute. This will give us actually some constraints on the scale of inflation. The other case is instead if the Peche-Quinn symmetry is broken after inflation. This means, of course, that the scale of inflation is lower than the Peche-Quinn symmetry scale. In any case, but we see that this happens also in the other case as well. But this is the case where, in some sense, you have the formation of these domains with different values of theta after inflation. And in principle, depending exactly when this symmetry breaks, you have practically different patches, and the size of the patch is usually the Hubble parameter at that epoch. So you have, if you want, different domains with theta E, with different values of theta E, and therefore what you have to take, it's probably if the size of the domains is sufficiently small, you have many different domains within the universe. So what you have to consider is not theta one single value of theta, but the average. So take the average, and actually you need the average of theta E squared, okay? And this is one thing we will see in a minute. Of course, if you break the Peche-Quinn symmetry after inflation, you have also the formation of defects and also for, in principle, inhomogeneities in the axion field, which give you mini clusters. So I write here defects, and we will discuss it in a minute, and axion mini clusters. Okay, so let me spend just 1 second to discuss the first scenario and the second scenario just for completeness. Of course, this, as I said, is a bit connected to inflation. So I hope I will not go too much into what Chris will discuss next week. But of course, I mean, maybe there is also a connection, and it's also nice to see. Of course, so in the scenario 1, where the Peche-Quinn symmetry is broken before inflation, I told you that the axion is massless during inflation, so it's an additional degrees of freedom which is massless. So in inflation, you usually have the inflaton, which is pretty much light and massless, so you treat it as a massless field. And here you have practically the axion, which is not the inflaton. And so you have two massless fields during inflation, and this allows you to produce isocurvature perturbation. So what does it mean, isocurvature? Isocurvature means there is no curvature in some sense, but there is still a perturbation. And you can, in some sense, see this in this sketch here. If you have a curvature perturbation, the idea is, for example, assuming you have a fluid in a glass. So a curvature perturbation would be that the fluid has some inhomogeneities, and you have in some sense some different levels, for example, or some wave on the surface of the fluid. And this is exactly what you would determine to be a curvature. And you see, this is the only thing you can have if you have a single fluid. So let's write here, single fluid. Instead, the isocurvature can happen if you have two fluids. And for two fluids, you can have also the case where you do not have any curvature. So you have no fluctuation, if you want, on the surface, but you have a fluctuation on the separation between two fluids, the two fluids. Or if you want, what happens is, in this case, the axion fluctuation is compensated by the inflaton fluctuation and vice versa. So the total fluctuation can be zero, but the two fluids in it, the single fluids have a fluctuation on their own. And it's clear, as I said, this one you can always have if you have if you have more than one field active during inflation, massless. So the fluctuations are usually coming from having a very light field. And during inflation, usually the fluctuations are coming from the Hubble parameter. So you can get, yeah, I guess you will see this discussed next week.
Can I ask you a question?
Yes.
For the isocurvature case, to cancel the it must be the fluctuation mode of the inflaton and the axion must be the same. In that case, we can cancel each other, right?
Well, the pure isocurvature, yes, it's of this scenario, but of course you have both. We will see a minute. So if you have two fields, you can assume you can have one mode that you define as the curvature perturbation, and you have then one mode which is the isocurvature perturbation. So in the real universe, you will have both. You do not have only pure curvature or pure isocurvature. So in that sense, I was showing you here, this picture is for the pure isocurvature.
Oh, my point is, take the cosine function as an example. In order to cancel these two sine or cosine functions, the frequency must be same, but the phase is random. In that case, we can cancel. If two sine or two cosine functions, the frequency are different, it cannot be cancelled. Just like the sound. There are too many sounds,
but for the fields are two massless fields. So in some sense, you can develop them into, if you want, Fourier components, and you have a component for the same frequency from each field.
Okay.
So the frequency is not a problem. I mean, it's as usual. You have the discussion we had also in the first lecture. You have to develop in Fourier components. For every Fourier components, you have both a contribution from the axion and one contribution from the inflaton. So this is not a problem. And also generically, of course, you have both. It's not that you can switch off the curvature perturbation. So this is exactly what I will give you in a minute as the limit. If you have two fields, you can always write the fluctuation in the sum of two components, one component which correspond to the curvature mode and one component which correspond to the isocurvature mode.
Okay.
And then, of course, also there are other effects that maybe Chris will discuss next week. I don't know. I don't want to go into it, but the isocurvature in some cases can be transformed into curvature perturbation by a mechanism like the curvaton, which I don't want to go into now. What I want to discuss now is only the fact that we know that from the CMB, the isocurvature component is actually small. So we do not, we have to impose that this contribution is actually small.
Okay.
For the case where we have an axiom going massless during inflation.
Okay.
So, and this is exactly the constraints I want to look at. So let me just derive it very quickly. So limits from CMB on isocurvature. So the isocurvature behave different so it give you in some sense a shift in the peaks and the slightly different form. So that's why you can put constraints on it. And for example, you get constraints that the ratio of the isocurvature over the total curvature, so curvature plus isocurvature fluctuation, here is for the power spectrum, has to be less than something like 1%. This is from Planck 2018. I mean, it's a bit slightly larger the number, but let me take 1% just for simplicity to make things a bit easier. Now we have done now to estimate what is this as a curvature component, and I told you the fluctuation of the field is of order Hubble, and the size of the field, so the value of the field can give you. So if you want, we can estimate these with the square of delta phi over phi. And delta phi over phi, delta phi is of order Hubble, as I told you, and phi, of course, is of order Fa. So we have here something like hi squared divided by 4 pi square Fa square. And in principle here you would also have the theta I if you really want to take it. And if you take it small or large, then you have to be careful. But I will take it to be order 1. So I will take Fa here. And this is, in some sense, the prediction for the isocurvature. For the total power spectrum, you have also from CMB, assuming on the large scales, you have something like this. The total power spectrum is something like 0.2 10 to the minus 8. So if you put these two together, you see that this quantity has to be less than the total, so you get constraints from the Hubble parameter during inflation. And this has to be less or equal, and I just give you the final result without doing the computation in detail. It's a 10 to the minus 5. Well, you have this 2 pi factor and Fa. So this means that you need to have inflation sufficiently lower than the scale of the Peche-Quinn symmetry breaking. Of course, I mean, in this case, the breaking of the Peche-Quinn symmetry is before inflation, so it could be pretty natural that H is less than Fa, but you have a factor 10 to the minus 5. And you remember, for having the right dark matter density, Fa is order of 10 to the 12 GeV. So you multiply by 10 to the 5, it means the scale of inflation has to be less than 10 to the 7 GeV. So it's a pretty low scale of inflation. And in some sense, it's already telling you, for example, that you will not be able to measure gravitational waves or things like that, because the scale of inflation has to be pretty low. And also, of course, if you have a low scale of inflation, you have also a low scale of reheating, a low scale for the highest temperature in the universe. So in that sense, that's all you have to construct if you want a consistent cosmology. And in some cases, of course, it could be difficult to do also the baryon asymmetry, to produce the baryon asymmetry of the universe and similar. But of course, it's not excluded. And this is one scenario. And in that sense, you could, as I said, work around here with different models trying to fit everything. And note that here at the moment, I'm not specifying anything about the inflationary model, of course. Just as I mentioned here, if you would have here the theta initial angle, or here you would get also theta initial angle. So taking the theta to be less than 1 would actually makes the bound even more, if you want, more difficult to satisfy or more stringent. Okay, so this is the constraint you have for the first case. For the second scenario, where you take the average, so that would be the scenario 2. So this means the Peche-Quinn symmetry broken after inflation. Then in some sense, as I told you, you have actually to consider as a theta E is nothing else as the average. So the square root of the average of theta E squared. And you can compute these from, you assuming it's a flat distribution between 0 and 2 pi, you get that this is a value which is not so small, it's pi over square root of 3. So in that sense, this is again something a bit larger than 1 even, but not much. And it sometimes is a fixed value. So you have a less dependence on the initial condition because this is only one number. And in that sense, you are a little bit less dependent or less sensitive to any initial condition. Of course, in this case, you don't have any isothermal perturbation because isocurvature perturbation, because you have that there is no axion really during inflation, because the Peccei symmetry was not broken. So you would have to consider the field, the total field, the S that we introduced, for example, yesterday. So it's not, which is not massless in generically. So it doesn't have to be, it's not an additional degrees of freedom during inflation. So let's say in general, no isocurvature. Of course, I mean, you could have other things in inflation, but at least not the axion. But what you have is, of course, that if you break the symmetry after inflation, you have a formation of defects. So and the defects are of two types. Of course, since you're breaking a U1, the natural defect to form is a string. So you have actually strings for sure, always. And in some cases, you could also have domain walls. And these domain walls are present only if you have more particles. If you remember yesterday, you generically had a contribution to the anomaly for every field in which is charged under the Peccei symmetry. So if you have more than one field charge under the Peccei symmetry, you have a factor of n. So this factor of n actually shows up, sorry, I should have added here in the potential. So here in principle, you could have a factor of n depending on the number of fields. And this is the number charged under the Peccei symmetry. And of course, if you have an n here, then the cosine in principle has many minima within one period between 0 and 2 pi, in particular exactly n. And this means that you can have also the value of the field to be on different sides, and you have actually really domain walls between these two different configurations, with the value of the field on one minimum and the value of the field on the other minimum with n+1 if you want. So, so this means that in that case, you can have also domain wall formation, and the domain walls are actually usually a very big trouble. So because they often dominate the energy density of the universe, and they give you the wrong behavior of the Hubble parameter, and they are quite difficult to get rid of. So strings usually move around, they will at the end reconnect and decay into axions. And when they decay into axions, of course, one prediction is that they would produce more axions. So in that sense, the population we discussed about coming from misalignment is not the only one you have. And indeed, recently, there have been actually a long discussion and a lot of different results for the contribution coming from strings decays. And there were groups saying that that would be small, groups saying that would be larger than the one coming from misalignment. Indeed, also a very recent paper of the group of Villadoro, I think last year, was saying, for example, that you could have a contribution coming from string, which is a factor of 10 larger than the one from misalignment. And of course, in that case, you have to take into account that contribution. So in that sense, if you want, strings can give more axions, even a factor of 10 more. But this factor is very uncertain. And this is why in this scenario, usually the prediction for the axion dark matter, in some sense, it's not there. Even if you can pin down theta to be exactly pi over square root of 3, you still have this uncertainty about the strings. So this means you have to be a little bit generous, and you can have, in some sense, a region in the parameter space which could give you the right number density and the energy density of dark matter. And you cannot really say it's only one point in parameter space or one value of FA, exactly because there is this uncertainty, unfortunately, about the string contribution. As I said, it's a long story. Many computations have been done also in the past, and more computations have been doing, people are doing those now. The problem it's usually that it's very difficult to do this computation. You have to do it through numerical simulations, and you have to simulate really the string formation and then the string evaporation into axions. The problem also is that you have very different scales in the problem. You have the horizon scale, and you have the size of the string and the size also the thickness of the string. And the thickness of the string is usually 1/FA. So this is a very small scale compared to the horizon scale. And it's very difficult to have a numerical simulation covering practically this huge range of scales. So that's why we have not yet really pinned down the numbers for this string production. But let me just mention 1 second the thing about this domain walls. The domains walls, of course, as I said, they are very dangerous, and they do not usually decay or recombine so very easily, because also they are separated by quite distances in the universe. So the only way to get rid of them is usually to have them decay. And to have them decay, you need to break the Peche-Queen symmetry additionally with some other terms, so that at the end, if you want, you modify the potential, and there is not, the vacua are not all degenerate, so that you have only the vacuum at 0 if you want, that is preferred, and all the rest are a little bit less preferred, so that you can at the end decay. So the additional domains where you end up with theta different from 0, you would actually have them shrink in the evolution of the universe, and at the end yes, practically you end up with only one value and one, if you want, big domain. But in some sense, this one is still also unclear how to do that. You can add an additional term to the potential. I don't want to discuss it very much in detail here, but in some sense it's an additional complication. So if you want to remain simple, the simplest solution is just to take n equal to 1. So only one field charge under the Peche-Queen symmetry, and then you are, in some sense, you do not have this problem to start with. Okay. So this one was one thing I wanted to cover. And then now I have, before going to the slides, I have just also promised yesterday to tell you about, of course, the lifetime of the axiom, because you also would like to be sure that your axiom is still around today and did not decay. So let me go to the issue about axiom decay. And as I told you, the main, of course, the axion is very light. We saw the FA is order of 10 to the 12 GeV. This means the mass of the axion is of the order of 10 to the minus 6 or so electron volt. So it's very difficult for such a particle to decay because it's very light. So if you want, axion dark matter is very light. So the only particle it can decay to is, of course, photons. And of course, you have, in principle, a vertex. We saw it that you can write this FF dual term with the electromagnetic field. And also you have the mixing with the pion. So in principle, also, if you would not have completely that term, you still have some rate, because you have, in some sense, the direct coupling of the axion to the photons, which this would be this FF dual term in the Lagrangian. But you also have the decay connected to the mixing with the pion. So let me write the pion differently because it's a composite field. And of course, the pion also decay into 2 photons. So in that sense, even if you would start with the model where the additional Peche-Queen charge field do not have any electromagnetic charge, So then you would not generate this coupling, but you do generate this anyway. So at the end, you have generically a decay of the axion into 2 gamma. And we can very easily, we can parameterize this unknown coupling. So the coupling which is here or here, we can say it is parameterized by a Ca gamma gamma, which is in some sense a quantity which gives us the total value of these two, and it's usually, as I said, non-vanishing. And then I can just write down the decay rate for this process, which is just coming by the vertex. So you have a C square A gamma gamma. Here I would use this with the usual suppression of pi Fa, and here I have an alpha QED, just for consistency with the other coupling of the gluon. So I write here alpha QED squared, and I have some factors of pi's and 2b from the decay. And I have an Fa squared, and of course I have an mass to the cube. But for the QCD axion, again, the mass and Fa are related, and this means that this Fa you can rewrite using lambda QCD and the mass, and at the end you get something which goes like the mass to the 5th power. Remember, Fa is 1 over mass, so you add the 2 powers of the mass, and this means it's a very strong dependence on the mass of the axion. And the fact that the axion is also very light means that the decay rate is very, very long. And indeed, we can put in numbers. So I give the numbers now for the decay. So the tau, so the lifetime
Sorry, may I ask a question?
Yes.
So the previous formula for the decay rate is assuming both Feynman diagrams to be at 3 level. Is that correct? No, or an effective coupling at 3 level?
Not at 3 level, but whatever they are. So this diagram, if you want, you could have here a triangle of the heavy quarks we had before.
Mm-hmm.
But I don't care. At the end, this gives me this Ca gamma gamma. So this Ca gamma gamma is actually the number which takes into account the computation also of the loop.
So this factor would include the mass of the pion, for example, or?
Yes, if you want, but this is actually not so, yeah, you include it if you want. It's at the end, though, the important scale is always Fa. And here you see it immediately because here you have the loop and the particle in the loop, if you want, get a mass of order Fa. So if you compute this loop, you get a 1 over Fa. In this diagram, actually, here you have the mixing, and the mixing is mass of the pion divided by Fa. Multiplied by 1 over mass of the pion. So the mass of the pion in the end is not so incredibly important.
Okay.
But you can compute it exactly. So you can find it in the references, and this is again, but the form and if you want, the suppression of the coupling is always 1 over Fa.
I see. Okay. Okay. Thank you.
Yeah, and indeed, also here, this Ca gamma gamma, in some sense, as I said, the Fa, if you want, you define it initially as being connected with the coupling to the gluons. But at the end, it's also the order of magnitude of the coupling to the photons. Apart from this factor Ca gamma gamma, and this factor, of course, can be different. But for typical model, it is of order 1. Recently, there have been also models trying to increase it or to suppress it, of course. Of course, if you increase it, this means you can see the axiom even better, also especially in experiments. We will get to that in a minute. So that's why some people were trying to build model where you could, in some sense, enhance this Ca gamma gamma coupling. On the other hand, you could try to think, okay, if you want to really have an invisible axion, I can suppress it. But usually the suppression, I mean, it's very difficult to suppress it because you would have to really cancel these two diagrams against each other. So in that sense, you would need a really very strong fine tuning, and generically you can have it of order 10 to the minus 1, this Ca gamma gamma. That's not a big problem, but if you want to have it much, much smaller, you need to tune, okay? Yeah, okay, so thanks for the question. I think it's important. So here is not the mass of the pion which gives you the decay, yeah, or the pion decay constant. Okay, so let me get to the numbers. So I have a tau, so really the lifetime, A into 2 gamma. And I can, putting in numbers, I get something like 3.65, 10 to the 24 seconds. And this is just taking Ca gamma gamma to be 1. So here I have a 1 over Ca gamma gamma. So it could be larger or smaller depending on what you put here. And the mass I took to be electron volt. Okay, so this is actually much larger than the mass I have in the case of dark matter. And if you want, I can also scale this one with the age of the universe. And you see that this is something like 0.8, 10 to the 7 times the age of the universe. And again, the same factors. So here, of course, if you take the fact that the mass of the dark matter is 10 to the minus 5 electron volt or 10 to the minus 6, for the case of dark matter, you see that you get a huge suppression. So you really don't have to worry about the axion decaying today. So in that sense, you would never see this decay, or you have to really wait a huge amount of time. And the only problem in this case is if the mass is above the electron volt. So if you have 20 or 30 electron volt axion, then you could have expected the decay to happen now. And in some sense, this is also one constraint you have to put in your model. So if you would look, for example, at a thermal axion, you have a bound in the sense that if the mass of the axion is too large, then the particle would have decayed already. Of course, this is not a problem. If the particle is not a dark matter, it can decay and you can live with it. And it can solve also the Peche-Quinn problem of QCD without being the dark matter. But for other purposes, you have in some sense, if you want to be the dark matter, then the mass in some sense has to be less than a few electron volt, or 20, I think, or something like that. Okay, so this means, okay, for axion dark matter, the mass is of order 10 to the minus 5 electron volt or so, or 10 to the minus 6. There is a range. We will see it in a minute in the figure. So therefore, the lifetime too long to see. Okay. And in some pictures, of course, this argument, you can again extend it to the case of the Alps. So for the Alps, of course, you don't have the relation between, oh, sorry, I had already, I jumped to one page. Oh, okay, I will use it later maybe. So in this case, of course, this formula is correct also if you have an Alps, which couples to gamma gamma. Then, of course, the mass and Fa are two independent parameters, and you have just to plug them in here to get a lifetime. But of course, usually also in that case, the lifetime, you can put a constraint in your parameter space, and we will see it, I think, in the figure I will show you later on. But generically, of course, if you are with low masses, you don't have to worry about this very much. I mean, you have usually very, very long lifetimes. Okay, so this one is practically the last thing I wanted to do. No, actually, there is another thing I wanted to discuss since, yeah, let me just the final discussion on the tablet. Of course, there was a question also yesterday about seeing these oscillations. And so I just give you also the expression for the axion oscillation frequency. This is again connected to the mass. And this is again, you can rewrite it as 2.5 gigahertz. So it's a very large frequency for masses of the order of 10 to the minus 6 electron volt. So this is exactly for the region of the dark matter. So you see that the frequency is very high. So in that sense, if you are not able to really disentangle such high frequencies, what you see is just the average, and the average is 0, so you do not have any theta contribution and any, for example, electric dipole moment. So in order to see this instance contribution to electric dipole moment, you have to go down to very low, so very, very fine resolution in time in order to see these frequencies. The other thing I want to also compute approximately is the de Broglie wavelength. And for the de Broglie wavelength, of course, you know the expression. You have h divided the momentum, or in this case is a non-relativistic particle, so I write the mass times some velocity. For the velocity, I assume that in the galaxy, we have again velocity similar to the WIMP, so something like 270 kilometers per second. And then if you plug this in and you also put the mass, you have something of the order of 10 to the 8 meters, if I correct. Oh, I didn't write the, oh, very bad. I didn't write the units, but I think it is meters. Electron volt divided by mass. So it's a very long de Broglie wavelength. This means that also in your experiments, generically the axion is not really a particle in the sense of we are used to in particle physics. It is a field, and it's really, in some sense, is extending in a huge wavelength. And of course, if you have the mass, which is very, very small, this is going in the direction of these ultralight axions. Then of the order mass of the order 10 to the minus 20 electron volt, then of course you have macroscopic sizes equal to dwarf galaxies or something like that. And in that case, then you can in some sense explain also the fact that you do not have structure in the universe at very low, small scale due to the fact that the axion cannot have such a structure because it becomes a quantum mechanical object if you go to a wavelength smaller in some sense than this de Broglie wavelength. So, and in that sense, I will show a picture later on where people did simulations. So this goes in the direction also to having these axion stars, as they are called. So if you have also a collapse of axions, also within the mini clusters, you form sometimes these solitonic objects in the axion field, which have sizes which depends, of course, on this de Broglie wavelength, and they do have this a kind of quantum structure, and you see it also in the density in some sense that you have some kind of wave-like behavior. I will show it in the picture in a minute. So in that sense, it's a little bit different, of course, also to simulate these very light axions in comparison to simulate, for example, the dark matter. For simulation of WIMP dark matter, people use, of course, particles. If you want, you can consider the code as looking at what happens where you have a number of particles moving in the universe and not interacting in some sense. For the case of the axion, especially if it is ultralight, you cannot neglect these effects coming from, these quantum effects coming to the fact that the de Broglie wavelength is very large. So as I said, you cannot really interpret it as a particle in very many cases. So it's better in many cases, also in the experiments, to interpret it as a field instead of as a particle. Okay, so this one is something I wanted to just show. Just for highlighting the difference. And also, I mean, as a particle physicist, and I don't know if most of you are particle physicists, I guess, we are not used really to think at such type of particles where the Broglie wavelength is really macroscopical, okay? And the axion is that type of particle, even if you have a mass of only 10 to the minus 6 electron volt, still the de Broglie wavelength is large. Okay, so this one is what I wanted to say, and on the tablet. If there are any questions, I would take here the short break about questions.
Could you repeat the explanation about this de Broglie wavelength and the the axion cluster. I didn't catch your meaning.
Well, we will see it more in detail the next in the slides. I will show you a picture. The point is that if you have an object with a large de Broglie wavelength, you cannot treat it as a particle. Okay, so
Yeah,
when we describe usually particles like also matter or any particle in particle physics, we assume the de Broglie always that the de Broglie wavelength is in some sense smaller than the size of the particle, or okay, even if you are pointwise particle, in some sense we do not have to worry about overlapping. For example, the de Broglie wavelength of two particles overlapping apart from where they are really scattering against each other. Okay.
Mm-hmm.
So in that sense, you don't have any interference effect, if you want, among different particles or things like that. Instead, for the axion, it's different. And indeed, for example, we'll see it in the picture of the simulations. When you have an axion star or an axion core in the middle of an axion mini cluster, you have this interference pattern there.
Okay.
And in some sense, when you do the important point I wanted to bring across is that when you do the simulations, you do not simulate the axion as a particle, you simulate it as a field. And it's also a completely different way of doing the numerical simulations.
Oh, okay.
Okay, I don't see any other questions. So let me save the slides before I forget. Okay, so I would stop here and go to the slides. Yes. Okay, so here I have put together a few slides to show you, as I said, a couple of pictures, and I will try to, let me see if I can put, yeah, the problem is if I do full screen then I lose the pointer, which I don't know why exactly, but let me keep it like that if it is visible enough. Yes, so here is just the review slides of what we already had. Here you have also some names which I didn't give you completely. So in the papers, you can also look at the Peche-Quinn paper is of 77 and Weinberg-Wilczek is also of the same year, just immediately after. As I already told you, this is the coupling which solves the Peche-Quinn, through the Peche-Quinn mechanism, the strong CP problem. And gives you in some sense the coupling to the gluon, but we saw also that you can have in principle also other coupling to the photon. Here is again the same slides about the generation, so this misalignment mechanism, and here with the correct potential also. And as again, in this case, you can consider really the evolution, but apart from what I discussed in the slide, on the tablet as a kind of estimate, of course, nowadays you can do numerical simulation. And here I'm showing some numerical simulation from a paper by Armanitaki, Demopoulos et al. A few years ago. And here you see exactly the evolution of the axion field, which was computed, of course, numerically. And you see, depending on the initial condition, you have different type of oscillations. And at the end, though, the oscillation becomes really a cosine oscillation, as you would expect from the solution we had yesterday. This P of theta factor, which is plotted here, is exactly the corrections you get to the number density and therefore also to the energy density connected to this, the fact that you have non-harmonic effects. So, of course, the potential is 1 minus cosine. So if you are on the top, you are not really having just a quadratic potential. And these effects you can see mostly if you start with very large theta angles. So here, for example, and you can in practice compute numerically this factor P of theta, which tells you what is the correction that you have to apply if you do start with a large theta. And you can use it in some sense for your prediction. So here in this expression that I gave you yesterday, in principle, you can add this P of theta, which takes into account these additional pieces. So the quartic, and in principle also you can do the simulation also with the full sine of theta if you want to get these corrections. Now, I didn't, as we saw yesterday, the FA to get the right number density is of the order of 10 to the 12 GeV, which is also good news because it's still allowed. Indeed, I have a picture later on and we discuss this. We have some constraints on FA and they come from the cooling of stars and supernova. Because of course, if you have the axion coupling to the standard model, in principle to the photon, but also to other particles, you would actually be able to emit axions from any astrophysical object, similar how you emit neutrinos. And these axions, as neutrinos do, they will just go through the whole astrophysical object because they do not interact practically, and they will bring out energy from the star or from the supernova. And this, in that sense, changes the time of cooling. And from that, you can put quite strong constraints. Here I have a text which is wrong. So you can have strong constraints on this value of FA. And this is already telling you that FA has to be larger as something of 10 to the 9 GeV. So it has to be an intermediate scale. And if you want to have a limit by the dark matter density, you then have just a window for the axion, especially for the axion connected to the QCD. So 10 to the 10 GeV to 10 to the 12 GeV. And then, as I said, you translate it into a mass. You see that it means the mass is around 10 to the -5 or 10 to the -6 GeV, sorry, electron volt, of course. And actually, you can see it here in this plot, which I stolen by a review paper by Bela Majorowicz on Admx. Here he was really highlighting. So first of all, I mean, due to the relation between MA and FA, in this plot, usually this is the generic axion plot where you plot the mass on the horizontal axis, and on the vertical axis, you usually plot the axion photon coupling. Is this CA gamma gamma I was telling you before, but including the 1 over FA. So this is actually, it's GeV to the -1. So if you want, this one is 1 over FA. And you see that therefore, if you are really solving the QCD problem, you are actually in a band because you have this relation between FA and the mass through lambda QCD. And it's not a single line because, of course, you have again this uncertainty into this CA gamma gamma I was showing you on the tablet. So these it can change plus or minus 1 order of magnitude. So from 10 to the -1 to 10 to the factor of 10, and this gives you exactly this band, this blue band, if you want. Now, if you are within this blue band, you would solve the strong CP problem anywhere you are. But of course, to be the dark matter, you have in particular range, and these particular range are highlighted here. So here you have the pre-inflationary scenario, which was the scenario 1, and the post-inflationary scenario. I mean, here it's very generously, let's say, plotted because you have 3 orders of magnitude. I would probably keep it a little bit smaller, but nevertheless, you see that you have a range of masses and a range of FA, which will give you the right dark matter abundance. We will get to the experiments in a second, but you see that here there are also some experimental results. And here you have this line, which tell us for the Alps, and we will see it in a minute also a bit more carefully, the limit you have where in order to have a good dark matter candidate. As I told you before, you can repeat the same misalignment argument also for the Alps, and if you don't want to overclose, you have to be below this line in practice. And that's similar. In some sense, you have more freedom, so it's a bit shifted with respect to the band you have for the QCD axion, but it's still, yeah, it's still there. So there is still a limit you can find. Indeed, I mean, I have also here the plot of one of the papers. Here you can look at the paper where people really computed this cold dark matter for the Alp case. And in this red region here is the region where you can have cold dark matter. And this boundary of this region is a bit uncertain depending on, as I told you before, how exactly the mass of this Alp depend on the temperature and how exactly it switches on or if it switches on at all, etc. So this is a bit of the uncertainty you have. And here on this plot, you have also the limit here on the lifetime. So the lifetime of the Alp has to be, if you want to be dark matter, has to be less than 10 to the 17 seconds, which is the lifetime of the universe practically. So you see that in this case also you are already excluding the large masses because they will give you a strongest decay. And here you have also limits because you would also produce gamma, which will also be observable. For example, here you have bounds from X-rays. And of course, the limits we have here on top are experimental limits instead on the laboratory, which I will discuss very shortly later. And here, let me come again to this issue about mini clusters and stars. So the formation of mini cluster is also something which is being done also here in Goettingen. So I am quite happy to show this picture from a paper of a colleague of mine, Jens Niemeyer, which is here in the Astrophysics Institute, and he and his group are actually since some years studying this issue about axion stars and axion mini clusters. And in this case, the simulation is actually of such a cluster. You see it here. The sizes here are not so incredibly big. So here is not an ultralight axion. Here is an axion of more or less like the QCD type axion. And you see, nevertheless, that in the center, you develop a kind of soliton. So this very red region is a very high density. And here is the evidence I was telling you about the fact that you see the quantum nature of the axion. You see here these bands are actually some kind of interference pattern coming from the fact that you have here de Broglie wavelength, which are macroscopical. And this, in some sense, you see it in the density. So the density has a kind of wave-like features embedded, which is connected to these interference effects, which usually you do not have for dark matter, of course, if it is a particle and not a wave in some sense. Okay, so I hope this helps understanding what I meant before. Okay. And then I have a plot which tells you a little bit what is the constraints on this FA for the axion. So here you have again the axion scale in GeV. On the lower axis you have the mass, and you have the relation always between them connected to lambda QCD. So you see that for large masses or for low value of FA, of course you have a lot of constraints, and you have also some experimental bounds. You have on one sense these constraints which are coming here, super K, SK, or from supernova, and the white dwarf for globular clusters. These are again connected to this cooling mechanism for stars, which I was mentioning. And here in the parentheses, you see the coupling, which is playing the dominant role in this limit. Here, for example, the coupling to photons. In some cases, also the coupling to electron is playing a role. And then you have also other constraints. So from the cosmology side, of course, you have constraints from also nucleosynthesis and the cosmic microwave background. In some sense, here also the fact that you cannot have hot dark matter, as we just discussed also yesterday. And these already excluded the relatively masses above the 1 electron volt or so. The nucleosynthesis bound, of course, connects to have additional degrees of freedom in radiation, and also the CMB constraints is also connected the fact to the decay, of course, of the axion. If you have too many axions decaying, they would actually create an additional component in the CMB and distort the spectrum. But then you have also other type of experiments. And here, for example, what is here shown in green, these helioscopes. The helioscopes are, again, the experiments which try to measure the axion coming from the sun. So as we already discussed, the cooling mechanism would work also in the sun. So the sun would continuously emit axions. And in principle, if you point a magnet towards the sun and try to see if there is any transformation of these axions into a photon. So this brings me to the main coupling and also the main ways to detect the axions. So the main if you want, a variable or the main coupling, which is actually used for trying to detect the axion, is of course the coupling to the photons. We saw it here with the coupling with 2 photons, but actually one of the photons could also be a magnetic field. So a classical magnetic field like is pointed here with an X. And in these already telling you that if you have an axion entering a region with a strong magnetic field, it would actually change into a photon. It can oscillate into a photon. And this is called Primakov effect. And this is one of the main mechanisms used for trying to detect the axion. So for example, as I told you, if you have a magnet and you point the magnet towards the sun, you could hope that the axion coming in this, from the sun enter this very strong magnetic field and then get transformed into a photon. And you can try to look for these photons. And in principle, the evidence, of course, would be just to have a photon showing up in your detector without having any other, so yeah, from nothing in some sense, because the axion comes actually from the sun. So in this way is one way you could detect axions from the sun. And of course, axions from the sun do not have to be the dark matter. So they can be also in mass ranges which are higher than the mass you have for the dark matter case. And this is why these constraints indeed is at the moment excluding masses which are not interesting for the dark matter, but they could be still axions which solve the strong CP problem. Here I forgot to say, of course, here is the region where you have the cold dark matter. And here again, you have the post-inflationary and the pre-inflationary range highlighted. And in this pre-inflationary Petroglyph phase transition case, of course, it depends on theta I, so the initial angle. So if you put the initial angle to be very, very small, you could push the scale also to much higher values than 10 to the 12 at the cost of a fine tuning. And also at the cost, of course, you remember, you have also even stronger limit on the inflationary scale because you get this limit on the isocurvature, which would depend in part also on theta I. So, so you see, practically these are the same ranges you had in the previous picture, perhaps a little bit less generous, especially the post-inflationary one. Okay, I want just to mention another experiment which is interesting, even if it does not detect really, for at least so far, dark matter. It's the experiments like the light shining through the wall experiments. In this case, you have to, in some sense, have 2 chambers with a magnetic field, and you try to do the process in both directions. So you start with a laser, gamma in the laser. You make it oscillate, or you hope that it oscillates into an axion. The axion then would actually go through a wall while the photon cannot. So in some sense here, you just stop any possible photon from the laser, but the axion will go through. And on the other side, you have a specular, if you want, apparatus where you have again magnetic field, and you hope to transform back the axion into the photon. And these type of experiments, of course, are sensitive only to, if you want, largish scale 1/FA, because here you have 2 vertices, if you think. So it's a process where you have both to produce the axion and to detect the axion. Instead, of course, if you use the sun as a source of axion, you save, in some sense, one of the coupling. On the other hand, of course, in this case is really more controlled because you are really experimentally producing the axion and detecting the axion. And one experiment of this type is, for example, the Alps experiment at DESY in Hamburg. And they are actually some of the constraints we were shown in the previous plot, which I think, let me see if it is here. Yes, the Alps 2 projection, for example, here. Okay. Of course, you could also have a different effect, which is called the birefringent effect. In this case, you don't really observe just the fact that the photon in some sense crosses the wall, but you see that the change of polarization in the plane, if you want, of polarization of a photon, which is also affected if you have an oscillation into an axion. And these DOSTAS experiments are done also in Italy. Actually, it's quite a, you probably, I think it's done in Padova or something like that. But of course, in this course, we are more interested to the dark matter side of things. For the dark matter side, as I said, you need actually to be more in this region. And here is another plot which I showed because, again, there is more the schematic. So laser experiment are experiment like this shining through the wall. These solar magnetic are exactly this experiment trying to see solar axions. There are telescopes in the sense that you can see again also this change of the photons from very far object if you have an oscillation into axion due to the presence, of course, of macroscopic magnetic fields also in the universe. And but important if you want experiments for dark matter are mostly these microcavity experiments, experiments which try really to measure the axion from the halo again into a strong magnetic field converted into a photon. And one of the leading experiments nowadays is this Admx experiment. And here I show a plot of some time ago because it's also still a little bit clearer than the present plots. This is a really long-term, if you want, experiment. So the experiment is only now, in some sense, touching this region where you have the cold dark matter. And note that the problem, of course, of this type of experiment is that you have to match, if you want, the mass of the axion with the resonance frequency of the cavity. Because this conversion from axion to photon, of course, works much better if you are exactly at the right frequency in your cavity, and you have an enhancement, if you want, of the signal. And to go to such a very small couplings, you need really to exploit that effect. And this means that you have actually to scan, if you want, every mass of the axion very, very finely to try to measure to see if there is any axion to photon conversion. And here are the published limit. Here there are some limits. I don't know exactly now at what point they are, but they are in some sense touching this region, and in principle they could detect the axion if it is in this area. As we saw in the previous plot, which I can show again, there are now planned experiments which would cover the higher region. So here you see here, for example, this MedMax experiment and project, which would plan to cover the higher region where you are more in this post-inflationary dark matter scenario. And yeah, and that is actually the future. So for the future, because the experiment is not yet, it's just at the level of being a proposal, and actually now I think they are trying to prepare some prototype. Okay, but this is not the only thing you can look for. You could actually look also at these effects connected to the neutron. So as we already discussed, you have this oscillation of the axion. And this means that this gives you actually also an oscillating electric dipole moment for the neutron. In order to see this effect, as I said, you have to really be able to measure very, very large frequencies to very, very small time intervals in order to be sensitive to this change due to the oscillation. But nowadays there are some experiments proposed to try to look for it. And another effect, which is maybe easier to see, and it's planned to be explored and searched for by the Casper experiment in Mainz, is, for example, this axion wind spin precession type of effect. The effect here is connected to the derivative coupling of the axion. We discussed them yesterday. And the fact that you have a derivative coupling means that if you have, for example, motion, and in some sense we have, because we are moving with respect to the halo, so we have a kind of axion wind, and this presence of axion wind will give you a coupling also for the spin of a particle in such a way that in some sense it acts a little bit like a magnetic field. And therefore, if you have a magnetic field in your experiment, you have a kind of superposition of two magnetic fields, and if they are not aligned, you get precession. And this effect could cover actually some part of the parameter space at relatively low mass. It's not clear if they will really reach the dark matter band. And another thing I didn't really mention a lot is this coupling to electrons. In principle, you could also have, of course, the coupling to the neutron has to be there in some sense, and it is there because of the theta problem in QCD. But of course, you could have also a coupling to electron through, again, if the electrons are charged under the Peche-Quinn symmetry, or through loop processes, even through the photon coupling, etc. And if you have a coupling to the electron, you could also have another effect, which is in some sense the absorption of an axion by an atom with emission of an electron. And this is another possibility to detect the axion, to have this absorption type of events. So in that sense, yeah, there are at the moment quite a number of experiments planned for the future to try to measure these type of particles. Okay, so I'm getting nearly to the end. There are also other issues about the structure formation, which I don't want to go into the detail here. The fact exactly, so for example, Sikivi, which is also one of the big experts on axions, was proposing also already a few years ago the fact that you could also have in structure formation and in distribution, if you want, of the dark matter of the galaxy, have difference compared to the case of the WIMP. The fact that you have places where you have caustics, so where the density in some sense becomes very, very large due to some properties connected to the fact it's a Bose-Einstein condensate. It's unclear if this is really the case, but yeah, in some sense, this would be another possibility to see a different also, if you want, distribution of the dark matter also in the galaxy, if we would be able to measure it. As I told you, it is a decaying dark matter candidate, but usually the lifetime, unfortunately, is very, very long, and the photon energy is also quite low, so it's probably difficult to measure. And the final comment, perhaps, yes, this one, in some supersymmetric model, of course, you could have mixed dark matter models. So not only axion and axino, as I'm writing here, but in principle, you could have both axion and neutralino. So you could have actually cases where you have the presence both of a WIMP and an axion. It's not probably very economical, and you could say this is not the minimal scenario if you want to do, but nevertheless, this is also a possibility. So in these lectures, I discussed two completely different candidates and two different types of producing the dark matter, but you could also have scenarios where both these mechanisms play a role, and where you have something more as I said, more complex and probably a kind of multi-component, if you want, dark matter, where you have both the axion and the WIMP, or the axion and an axino, which is more a kind of FIMP-like particle. Okay, good. So actually, I had planned also to discuss a bit the FIMPs today, but I had actually, I was a bit afraid that I would not have time to do it. So that's why I took actually out the slides. Let me see, can I find it? No, this one is not. Sorry, these are not the slides I showed the other day. No, I lost the FIMP. Okay, I can try to look for it. It's probably not so interesting. You saw the exercise, and the FIMPs, of course, are also something which is being studied. Yes, here it is. Yeah, I can show it then shortly. The FIMP mechanism is, as you have seen probably in the exercise this morning, is connected to have a particle out of equilibrium and producing it again through the interaction of the thermal bath. So you can have it produced by decay, or as it was in the exercises, also by scattering. And usually the characteristic of this FIMP, where you produce it from the thermal bath, and you have a coupling which is renormalizable, is that you have this property that you build up the density of the dark matter slowly from the mother particle decay, for example, or scatterings, so that at the end you do exactly the opposite, if you want, of the freezing out, and this is why it's called freezing in. So usually you go out of equilibrium, as you see here, and instead here you build up a density and you go again to a constant value when the mother particle start to decouple. In this type of model, you have not only this production, but often you have also production coming from if the mother particle decouples like a WIMP, you would then produce again another component of dark matter from the final decay of this particle. And this is usually called the super WIMP mechanism. And these two mechanisms, again, can also give you the right density of the dark matter. And they are always connected to particles which are much more weakly interacting than weak. But depending on the mass, you have a range of coupling and masses, and if you want also interact with the particular type of mother particle that can give you the correct density of the universe. So this is another, if you want, mechanism which is very, very well studied in the literature. And I just wanted to mention it here because in some sense it's also going beyond the two mechanisms I described so far. But it's again, in some sense, a story which you can describe quite precisely using, of course, the Boltzmann equation to solve for the number density of the particles. So it's a pretty predictive scenario as well. Okay, and I think I can conclude here. And of course, I have still 10 minutes or so for questions, I guess, for the final questions.
Okay, I have a few questions. Could you go to page 92?
Yes.
Okay, for the left figure, I mean, from the vertical exercise, it says the axion field. So this means this is the frequency of the oscillation of the axion field, right?
Yes, of course, is the axion field. Yes,
Okay.
of course, here I think it's rescaled by FA, so that the initial angle, if you want, here is always between 0 and then the 2 pi.
Okay. In your tablet, there is a typical number. Is if I remember correctly, it's 2.4 gigahertz, right? It's the so that's mean this frequency is 2.4 gigahertz oscillation frequency.
Yes, but here, of course, the frequency is different. Here is the initial, so the mass doesn't have to be the mass at today. This is practically the oscillation during the QCD phase transition.
So this curve mean today this kind of oscillation is 2.4 gigahertz, right?
Yes, also there I think I took the mass, what I don't remember what I took as the mass, let me say, yes, this was for 10 to the minus 6 electron volt of mass. Okay,
but from the figure, the amplitude of this oscillation is become much smaller and smaller, right? So my question is, will it stop at some time? I don't know, because the amplitude is the amplitude of the oscillation is become smaller and smaller, right?
Sure, the amplitude does become, so that's exactly what we discussed yesterday. It goes down, the amplitude goes down like the scale factor to the minus 3/2. So indeed, the amplitude of the oscillation becomes smaller and smaller the longer you wait in the universe. But nevertheless, it's still non-zero. So it's you have a non-zero amplitude also today.
Okay, non-zero. Okay. Okay. Then go to page 95. I'm confused with this figure. I mean, the colored region are excluded, right?
Yes, the top part is excluded by experiment because, of course, here the coupling, remember, here is GV to the -1, so this is 1 over FA.
Okay, my question is for the right region, is the standard ALP CDM. I mean, why the the lower region is excluded. It's
No,
not intuitive.
no, it's not excluded. The red region is the region where you have the dark matter, and it's not excluded. This region here is not excluded.
Okay. I thought that the colored region is excluded.
No, the top region is excluded, and also this green region is excluded. These are the limits from X-ray, so because the Alp would decay, and even if decays with a lifetime longer than the universe age, it still gives you gammas and stuff like that. So you have a constraints on this part.
Oh, okay.
Yeah, sorry if I wasn't clear about that, but this red region is not excluded. This region colored on top, and this region is excluded.
Okay.
And this band here is the band, for example, of the usual QCD axion, and this region instead is the standard Alp. And actually, if you, in a sense, if you change a little bit the condition, you could also push it up to this region. So this pinkish region is also still not completely excluded.
Okay.
I would like to ask a couple of quick questions, if I may.
Yes, of course.
For example, in this plot, I see that the small mass that is shown is like the order 10 to the minus 9 eV.
Yes.
But I've also heard about some kind of particles called ultralight axions, ultralight axion-like particles, with masses that can be as small as 10 to the minus 20 eV. So I don't know if these kind of particles are related to what we've discussed today or not.
Yes, I mean, those particles are exactly what I mentioned, the fact that there you have a de Broglie wavelength as large as a dwarf galaxy.
Okay.
So
okay.
those particles are also being studied. There are nowadays some constraints, but for those particles, of course, it's a bit difficult theoretically to have those particles in the sense that you need really a tiny mass, okay, 10 to the minus 20 electron volt. This means also, if, of course, you could have, but you have very, very, very tiny breaking of this U1 symmetry in order to have such a tiny mass.
I see.
It's not excluded. There are some string models where you can realize that using suppression factors from volumes, etc. So I'm not saying it's completely impossible, but theoretically, of course, is a bit difficult to obtain very, very small masses. On the other hand, this band here, which is the QCD band, if you want, you could continue it further.
I see.
And also on the upper region, you can continue it in principle further, apart from this excluded. So in that sense, also for the QCD axion, the thing which is fixed is the relation between the mass and FA, but the scale at the end is not completely fixed.
Okay, so for this kind of ultralight particles, we would expect to get constraints only from cosmology and structure formation, not from these detection experiments.
It's very difficult to, I mean, FA, if you see FA here, but if it is a QCD type of particle, FA then has to go down to a tiny value. So, sorry, FA, of course, goes to a large value. That means the 1 over FA goes to a tiny value. So the coupling to the photon is incredibly suppressed.
I see, I see. Okay.
Yeah.
And regarding the slide that you showed on the FIMP and the super WIMP,
yes.
So well, there were this plot that yes. So from these scenarios, both the FIMP and the super WIMP are produced from the WIMP. So in this case, there wouldn't be any WIMP left. It would have decayed away. Is that correct?
Yes, in this case, the WIMP would have gone away, but you would have produced this other particle. And the problem, of course, this particle would interact much more weakly. So it's more difficult to observe, especially in direct detection, you will not observe it. You could observe it in indirect detection because it could decay actually, because again, it could be like the axion, it could still decouple so weakly that it doesn't have to be stable. And secondly, you could detect something, of course, at the LHC because you could produce this mother particle in the collider.
I see. Okay. Okay, thank you.
Yeah.
Hello.
Yes?
Yeah, Laura, this is Tanmay.
Yeah.
Yeah, so I have two things. So first of all, since the axions can couple with the electrons, so and the nucleons, so what is the current status on the bounds or on the couplings?
For the couplings to the electron and to the neutrons, unfortunately, I don't have a plot for that. Yeah, I can try to check if I find the reference. Yeah, usually people are more concentrated on the coupling to the photons. So the main idea in the basic models like the KSVZ and the DFSZ, the couplings are similar. So in that sense, you expect again, if you want a factor supporter 1 to modify a bit, but the scale is always 1/FA. But for really telling you the limits, I don't have a plot for that, and I would have to look if I find it, because I'm usually what is shown as the typical plot for the axion is usually as a function of the gamma coupling.
Okay. One more question is that is axion the only way to solve the neutron idiom problem, or are there any other possibilities to solve the neutron idiom problem?
Well, it is probably the only one which we have at the moment. Okay, there is the other solution, which would be, as I said, a zero mass quark, which is now excluded by lattice computation. And otherwise, of course, there is the possibility to generate this term only from at loop level, but that is usually not enough, because you need, I mean, 10 to the -9 is quite a strong bound. So this is one solution people proposed in the early days, but I think now is also quite difficult to realize. So at the moment, I don't have another proposal for a solution.
Okay. And suppose calculate the direct detection rate for the WIMP particles. You use the Maxwell velocity distribution function, right, for the dark matter?
Sorry, I missed what you said. There was a disturbance.
Okay. Now?
Yeah, try. It comes and goes.
Okay. So I am saying in the previous days, when you are explaining the WIMP direct detection rate.
Yes. Okay. Can go to the slides. These or this one?
Yeah, this is fine. Yes. So you use this AP as the Maxwell velocity distribution function. Okay.
Yes.
So I am saying, like, if this dark matter has some rotational velocities, so since it is in the galaxy, so like people have done any work by imposing some rotational term in the velocity distribution function to calculate the direct detection rate, or what would be the implication if we incorporate some rotation term in the direct detection rate?
Why rotation term? I mean, of course, we are assuming that the halo is practically moving together with the galaxy, so that you could have a rotating disk of dark matter. This has been studied. Or what you can have are streams of dark matter. Streams have also been studied in the sense that you could have some galaxy which, if you want a smaller one, which crosses our galaxies and get disrupted. And these would cause a kind of stream of dark matter. So this distribution which is moving in a particular direction due to this previous existence of a bounded object. And these has also been studied. So you can add, if you want, this additional contribution to this part, to this integration. And of course, if you move to highest velocities, you would get probably more signal. But at the end, the analysis that the experiment they usually do mostly for these Maxwell-Boltzmann distribution. One has also to say that the real distribution of the dark matter, as we can compute it from simulations, is not really Maxwell-Boltzmann one. So there have been also studied, trying to extend these to some other distribution. And this, of course, shifts a bit the limits that we have at the moment. And in principle, there have been also proposals how you could extract the distribution of the velocity if once you would have insufficient number of data. This, of course, is not yet possible because at the moment, we have only limits and not really an observation of the dark matter.
Okay.
Yeah, so, but generically, it doesn't change a huge amount the signal. So it does change the signal, but the point is also if you would have a rotational, so this dark disk, it's always like that you would not expect this dark disk to move in the same way as the sun in some sense. So at the end, you always have a non-trivial velocity of the dark matter with respect to the Earth. And you can, as I said, these are you would not expect to have all the dark matter into the dark disk. You need, in some sense, a more spherical distribution. So a disk, a pure disk of dark matter would not be stable. Like also the galactic disk is actually.
Okay. Thank you.
Okay. Any other questions? So.
Yes, I have a question maybe. So why are people so sure that the axion couples to the photon? Because this original scalar, it can also couple to a chargeless quark, I think.
As I told you, because it does mix with the pion in any case.
Ah, okay.
So, and I mean, if you want really to have a zero coupling to the photon, you really need to tune in such a way that the pion mixing or the contribution coming from pion mixing would cancel the contribution coming from the other particles.
Okay, clear.
And so, I mean, you can look in the literature, there have been some extension or some trial to see how far you can go with that coupling, both on the high side and on the low side. But of course, I mean, if you tune in such a way that the two diagrams cancel each other, you could in principle also get to zero, but it's a very fine-tuned situation.